Hello everyone. In this video we continue to develop methods to determine the number of solutions of a linear system without actually solving the linear system. In the last video we created a decision tree, and with this decision tree we are now able to determine the number of solutions a linear system has by examining its corresponding augmented matrix in row echelon form. Now, for linear systems with infinitely many solutions, we would also like to be able to determine the number of free variables. The number of free variables the system has without fully solving it. To do this, we explore more closely the relationship between the rank of the augmented matrix, the number of variables, and the number of free variables. Theorem 3.3.1 says that a consistent linear system in n variables with augmented matrix aug satisfies the following equation. So the equation is that the number of free variables is equal to n, that's the number of variables, minus the rank of the augmented matrix. Now there's a remark following this theorem that says that the equation in the previous theorem only applies to consistent linear systems. That is, systems with one solution or infinitely many solutions. So it does not apply to systems that have no solution. Let's go back to the previous examples we had and verify that this equation is satisfied. In example 3.2.11, do we have that the number of free variables is equal to the number of variables minus the rank of the augmented matrix? Well, the number of free variables was 2, and the number of variables was 4, and the rank of the augmented matrix was 2. So 2 is equal to 4 minus 2. And then in example 3.2.12, do we have that the number of free variables is equal to the number of variables minus the rank of the augmented matrix? The number of free variables was 1, the number of variables was 4, and the rank of the augmented matrix was 3, and 1 is equal to 4 minus 3. We can also verify that this equation is satisfied for case 1, when the linear system has one solution. In example 3.2.7, do we have that the number of free variables is equal to the number of variables minus the rank of the augmented matrix? Well, the number of free variables was 0, the number of variables was 3, and the rank of the augmented matrix was 3. So 0 is equal to 3 minus 3. And we would actually have exactly the same equation for example 3.2.8. Now let's look at example 3.3.3. We're given that each of the following augmented matrices in REF were found by performing elementary row operations on an augmented matrix corresponding to a consistent linear system. First, we want to verify that each linear system is consistent, and then we want to use Theorem 3.3.1 to determine the number of solutions of the system. In order to actually use Theorem 3.3.1, we need to make sure that the corresponding linear system is consistent. That's why we're asked to verify that the linear system is consistent. So in part A, we want to make sure that the linear system is consistent, and so we first find the rank of the augmented matrix. The rank of the augmented matrix is 2. And is that equal to the rank of the coefficient matrix? The rank of the coefficient matrix is also 2. Therefore, the linear system is consistent. Once we've established this, we can go ahead and use theorem 3.3.1. We can use the equation number of free variables equals number of variables minus the rank of the augmented matrix. So the number of free variables here is equal to the number of variables, which is 5. There are 5 columns to the left of the column of constants in the augmented matrix. And we found the rank of the augmented matrix to be 2. And so this linear system has 3 free variables. Since the linear system has at least 1 free variable, it has 3. That means that the linear system has infinitely many solutions. Moving on to part B. In part B, again, we need to start by verifying that the corresponding linear system is consistent. So the rank of the augmented matrix is equal to 1, 2. There are 2 leading entries, so the rank is 2. The rank of the coefficient matrix is also 2, and so therefore the linear system is consistent, and we can move forward and apply the theorem and use the equation in the theorem. So we can use the equation number of free variables equals the number of variables minus the rank of the augmented matrix. The number of variables in this case is 2, and the rank of the augmented matrix is also 2, and so the number of free variables is 0. A linear system that does not have any free variables is a linear system that has 1 solution.